So, hello everyone. Thanks for the introduction. In case anyone was still wondering who is that guy, I think probably most of you know me, but some may not. So yes, my name is Ralph. I work for Cernet. I've been here now for close to 10 years, I think. It's been a great journey. It's been a great time, and looking for another 10 years, maybe, Tom. So we can extend the protocol. There probably some work ahead for us. Maybe SMB 4 or something. Or do we want to skip versions? So we're probably just doing extensions,
That's
right?
That's a new dialect. I said don't go.
No, don't go dialect. So only extensions. But anyway, hopefully there's something to do for us in the future. Great stuff ahead. And in this presentation, I'm going to pick up one of the topics that Tom briefly mentioned, and which is well, where probably everybody is going these days, to the cloud. Maybe anyone here in the audience who is just currently dealing in business with moving workloads or stuff to the cloud, maybe raise your hands, not your heads, sorry. Raise your hands. I would love to know, is this something that is relevant here as much as I perceive it to be? And like Tom has said, yeah, things have changed. It's not like it has been like 10 years ago. So what spawned my journey into looking into what can we do to have Samba be a component in the cloud that allows us to do net use the cloud, and having Samba running in the cloud and allowing Windows clients to just mount a file system directly from your cloud, right? So the question is, how could that be possible with Samba? What would be needed? Maybe we can just use it as is. Would that be possible? What are things that might have to be improved or changed and so on? We're going to look into that, and we'll see that one of the components that Samba makes use of is a database, and Samba uses a CTDB database where hopefully everyone here is familiar with Clustered Samba, CTDB, has heard about it, because I'm late, so I don't have too much time to spend into some of the details. So in case there are some questions that you would like to have answered immediately, please raise your hand and I will do my best to answer those. So I have 46 slides in total, and I've been told that, lunch is afterwards, and I will just keep going, right? So everyone who's interested in learning all the dirty details, just stay here, skip lunch, and yeah, I will explain everything. The good news is that 30 of those slides probably are at the very end. You see, I added in outtakes, which is a kind of deep dive into a distributed database, which, as Volker put it yesterday, that's you can spend 6 months at the university reading about this and trying to wrap your heads around that stuff. So I'm just going to give a high-level overview of what's relevant for Samba in the context of being able, in the end, to having Samba running in the cloud, and having a Windows client being able to just net use it, right? So the goal is to have a cloud. You have Samba there. For a cloud, you probably have more than 10 nodes, 10 server nodes, or 20 or something like that. You probably are dealing with hundreds, right? And you're probably also dealing with, that would be the business goal probably, because the more clients, then the more users, the more money probably. So you might be dealing with hundreds of thousands of clients, and to have something that really, really scales, right? For this allows then Windows applications, you just migrate data to the cloud, and you can keep applications running unchanged, right? So this has requirements. You want to have this running all the time. It has to be fast. It has to be you need elasticity, you need be able to add or remove nodes in the cluster, and this must be a cheap operation. This should be something that should really be available. So you need something like multi-data center support in Samba to work with this, and multi-region support. And so Microsoft has something there, Azure SMB, where you can just net use the cloud. So let's see if we can get that with Samba too. So what would be the building blocks? From a very high level view, Samba uses two building blocks, essentially, when you're sharing files. Of course, a file system where your data is, and Samba uses a database. In the case of a cluster, it's a distributed database, right? And Samba uses CTDB there. And for this talk, I'm going to only deal with the database aspect of the things, right? Which is kind of makes it easy for me because the file system aspect is certainly also something that is going to be challenging to have a Linux clustered file system that really scales into hundreds or thousands of nodes and really scales out. There are several of them. Not all of them are open source here, GPFS for example, but CephFS, Gluster, and Lustre are. So for this talk, I'm going to look at the database only. So when thinking about what can I do to have Samba running on a really large cluster on systems, maybe on Kubernetes or something like that, I want to have 100 nodes, I want to have 1,000 nodes. The thing is, CTDB has its limitations, right? The original use case for CTDB was basically have something like a really high performance NAS running in a single data center, right? And this is not really suitable for cloud SMB at scale, whereas CTDB is maybe, I thought I have the numbers on this slide, or is it on the previous one? So you go back. Wonder where that, but there is. Yeah, so it scales maybe to 60 nodes and, probably gotta get my glasses on. 60 nodes and 50,000 clients or something like that, right? And one very subtle thing that CTDB does is it's a distributed database, but data is actually not replicated, right? So what Samba does, what we store in this database is file handle state. So, and for Windows applications, when they open a file, just to give you a better understanding of why this is important, most of you will probably know, but some may not. When opening a file, a Windows client can say, oh, there are share modes. So the Windows client can say, I want to allow other clients to open this file for reading, for writing, or for deletion, or they just don't want to allow this. They want to say, no, if anyone else wants to open such a file, just go away, anti-status access denied. Right, so in the server, we have to store the state somewhere so that all file server processes across the whole system can access this information, right? And so in case of CTDB, as data is not replicated, the data is just stored on the single node where the Samba file server process runs. So if that's the one that is crashing, that state is lost. So the protection of the file handle that might be, no, I don't want to share this file for reading, writing, or deletion or anything, is gone. Then there is some time while maybe the application and the Windows client is able to cope with being disconnected from the server. It attempts to reconnect, it maybe tries to reestablish its file handle, where it says, okay, I'm trying to, again now, to open this file with my share mode, where I say, I don't want anyone else to open this file. But there's a race, so at the same time, someone else might have come along, opened that file, right? We don't have that information in the database, so another client can open the file. It self-stores share modes that don't allow concurrent opens, and then you're screwed, right? So what do? So for that, we need the data replicated in the cluster, and we can't do that currently with CTDB. So we could try to improve CTDB, but I was wondering, I mean, these days, looking at the next slide, there are a lot of distributed databases out there already. This has started something like 10 or 15 years ago where distributed databases emerged. These are not all open source databases that I'm showing here. And the question is then, okay, is any of those maybe usable as a replacement for this specific use case, right? And then, okay, what do we really need from a database? What are really the requirements? Because if you start looking into what sort of performance or consistency distributed databases provide, it turns out it's a vast field. There's something called strong consistency and weak consistency, which means that you store something, but you actually might not read it back when you come back again sometime later and read that record, right? So I mean, most of us are maybe more familiar with an SQL server. You store something, you come back 5 minutes later, and you read it, and you think, oh, it should be there, right? But with certain databases, so-called eventual consistent databases, you might actually get back old state and not what was recently written, right? So for Samba, we need a database with strong consistency guarantees. And for a key value database, that means we need linearizability, which is the technical term. And for transactional databases, that means strict serializability. To implement locks, we need either transactions or atomic compare and set. And we need the linearizability and strict serializability for data consistency. As mentioned, for this thing, we have concurrent opens, and you have one client open a file and goes away, crashes, and so on. But we also needed to implement locking, because in Samba we need to use locking to basically serialize and isolate access to two different resources in the low level, from the file system and from the database, right? So when we get a request from a client to open a file, we have to do two things, right? We open or create the file, and we also have to store or update the record for that file that stores this file and the state in the database, right? And these are two separate operations in two separate resources, right? And we must make sure to isolate one client doing these two operations from another client doing these two operations, so they don't step on one another. And for this, we use locking. Some distributed databases support locking, but not the way we would like to, so it's possible to implement that on your own, on a distributed database, and that's what we would use. So for performance, you will see that in a minute when I have some graphs of performance comparison. CDB is just screamingly fast, and it can be screamingly fast because it just doesn't replicate. It just stores on a single node, which is just a local operation, and then it says, okay, I'm done, right? So this gives this high performance which is important, of course, for many use cases. But is it really important for a use case where you have this net-used cloud, right? Where you have maybe a company with offices spread all over the world, and you have there just some business applications like Word, and then a user just wants to open a file for editing a Word document. And it probably doesn't really matter if that takes. It's going to be slow anyway because it's going to the cloud and over the internet. So maybe it takes half a second, and if that's maybe 100 milliseconds slower, it probably doesn't really matter. And so it depends on the use case. So assuming that for this use case, net use the cloud, maybe it's tolerable to have the database component itself slower, right? And looking at from a theoretical perspective at how distributed databases are implemented, typically such strong consistent databases, they use certain protocols, so-called consensus protocols, and those are 30 years old. The first of them appeared in the 80s. The first one was actually view-stamped replication. Another one that probably everyone has heard of is probably Paxos, which appeared. I mean, they were probably worked on actually at the same time. Is Paxos, and there are other ones. The thing with those is those are all protocols that use a leader, which means all requests to the database go through a leader. The leader then somehow consistency replicates all the records in the distributed database, then comes back, and then the operation is completed. It tells the client, okay, I'm done. And of course, this requires communication to multiple nodes. It might fail, might have to repeat this. So of course, this is slower for this single leader approach. So the expectation was, okay, this is probably eventually going to suck from a performance perspective. Maybe other databases out there, and there are not many of them, which do things differently, can do better, right? So I was looking at, okay, what's out there available, and from the databases, which database use which approach, and then I set out to actually run tests, set up clusters in our data center, a Samba cluster for running Samba, and then distributed databases with some nodes to test all the thing and verifying consistency and performance. So from the candidates, so for all the databases you saw on the first slide with all the fancy icons there, only a few remained that would actually be usable given those constraints. And those are the ones that I was able to test And this is Ceph, and Ceph has a so-called Rados layer, which can be used as a distributed database. That's Apache Cassandra, etcd, which is a distributed database used in Kubernetes. That's Scylla, which is a modern implementation, I think, in C++ of Apache Cassandra, which is one of the earliest eventual consistency databases written in something like 2008, which is written in Java. So that's C++. Oh, maybe it's faster. We'll see. And FoundationDB, which was originally fun. I think it was an open source. Oh, it's originally an open source project. At some point, it got purchased by Apple, and then 5 years later, they open sourced it again. So these days, it's a great open source project. And so with these 5, I was able then to set up Samba test cluster, set up test clusters for the distributed databases, and run some benchmarks, right? So what did I do? I was mainly interested in really hammering that critical path where Samba has to go out and talk to the databases. And that's mainly when you open and close a file. So in Samba, we have our SMB torture program, which we mostly actually used to do functional tests in Samba. But we also have a few performance tests in there, and this one got added by Stefan a year ago or 18 months ago or something like that. And that basically just goes in a busy loop, open, close, open, close, open, close, right? Open the file, close the file. And then you can configure how long you want to have that running, and the number of concurrent processes, right? So I started with 1, and then I doubled the numbers basically for going from 1, 2, 5, 10, 20, 50, 100, and I stopped with something like 500 clients because at that point my just smallish test cluster in our lab, it just came to a grinding halt because I only had limited amount of CPUs. I had quite some RAM. Although the whole cluster was backed by SSDs. The database nodes were actually quite beefy, 8 cores and 64 gigabytes of RAM. I specifically added that much run because I knew the Java stuff is probably going to need it. And I separately set up a Ceph cluster with 6 nodes in total, so 3 monitor and 3 OSDs. I only gave it 2 cores and 8 GB of RAM, and we'll see. Maybe that's the reason that explains the numbers, but I don't know. My assumption was so it has 6 nodes, and just writing and reading a VIA record, it shouldn't take too much. Maybe it's a bit unfair because the other one said a lot more cores, right? Yeah. So technical detail. Only the logging TDB, which is that's a database name, so it's our name for our database, logging TDB. Probably most of them have heard that, right? And that's the one that stores this file handle state that I've been talking about. And that one is a little bit different. I'm not putting that into this distributed cluster. It would require an additional database operation per open, but I just wanted to keep it simple. Just hammer only on one database and see what we get. So the results, simplified. FoundationDB is the clear winner. Everyone else. I mean, even FoundationDB, if you look at the numbers, so we are basically at 10% of throughput of CDDB, right? I'm going to share you a few nice graphs on the next slides, but that's the key takeaway here. It's going to suck, right? So for workloads where you have many open, close, stuff like that, it's going to take more time to do the open. You will have additional latency, right? But for the use case where you just have NetUser Cloud and you want to open an Excel file, does it matter? We don't know. So feature-wise, FoundationDB also has multi-region and multi-data center support, which might be some important feature if we want to really build something scalable in the cloud. etcd comes next. Not that bad. Throughput of FoundationDB. Ceph Rados is completely unusable. It doesn't scale at all. So I was quite surprised because I was assuming. So for this, using the key, so Ceph Rados offers you to use just a key value store. So you can have a database in Ceph Rados. There's an API for it, and that's probably just what Ceph itself uses for its metadata server when you're running CephFS. Anyone familiar with the CephFS, Ceph internals, who knows better? And please tell me if I'm wrong, but that's what I believe how it's working. So, I mean, we've worked with a few customers, and we've heard rumors that CephFS, the file system, might actually not be really the fastest. So the numbers here pretty maybe go along with that. That it's slow and doesn't really scale. We'll see it on one of the next slides. And then for really contented workloads, so if CPU is really saturated, if I'm hammering the server with 500 clients, basically all about FoundationDB at some point. Not that they come to a grinding halt, but you get errors in the log, you get failures, then suddenly from the application where you have application errors in the Samba log where it says, so, oh, I didn't find the record in the database that I was expecting, I'm going to panic, right? And that was especially bad with Cassandra and Scylla. And etcd logged also worrying messages in the log saying that, oh, in the cluster of the database, it sends a heartbeat, right, for liveness checks. So all the nodes know that, hey, I'm still up and running. No need to tear down connection to me and assume I'm there. And I got messages like, so, okay, not being able to send a heartbeat for 6 seconds, right? And I was saying like, oh, okay, maybe etcd is not really tested. Let's put it that way, right? Not really tested to really be hammered by such a workload, right? And if you search for this message on the internet, you will find GitHub issues on etcd mentioning this. So it seems to be something that is common even for just when you have so running it in Kubernetes. So I don't know who of you is running Kubernetes. etcd is the core database used in Kubernetes for storing persistent state as a database in Kubernetes. You'll find lots of these messages if you search on the internet. So now finally some nice graphs. And I mean, I knew the numbers before I created the graphs, and I already knew that I was kind of going to cry in some sense. I always try to cheer me up with, oh, it's a different use case, right? So, but I mean, so the big nice one here, that's CityDB, right? So it's fast. But remember, it's not replicating. So if you want, anyone here persistent handles, knows that might be something that might be important. You can't do that with CityDB, the way it's currently working and why it's so fast. For that, you could use one of those, right? So it would be slow. Well, what can you do? So FoundationDB, you see, it comes on top of the other guys, right? And well, I wouldn't say it scales linearly. So the question would be then, where does it go here? And I mean, where does this guy go here, right? I mean, it has a limit that is probably somewhere in the region of the number of cores on the machine. As Metze pointed out immediately, he said, oh yeah, look, it's the number of cores, it's probably where the maximum is. Yeah, and that makes sense, right? The other ones, I mean, they keep going up as you're adding number of clients. So each individual request has higher latency, but you can get parallelism by having more clients and whatever the database does in the backend to have parallelism. But FoundationDB is really the only one that can keep going up. So you may have noticed there's no Ceph here. This was on a cluster with 3 nodes, non-concurrent opens, so basically all the opens were different files, right? Different files, that's important. So I did the whole experiment then again with a single Samba server, and so I had to do this because I couldn't get the Samba cluster with CityDB was too old to build Rados, the Samba backend with Rados, because it required a newer library version that wasn't available on that system. So I had to use a different system just to get that numbers. And I mean, where is it? There is it. So it's basically down there. I mean, it's 0. I mean, it's, yeah, could have done a logarithmic scale. So it's 50 or something like that. And goes down, which doesn't, also, you can't see that. It goes down, it starts at 50, and then maybe it goes up to 55, and then it goes down to 40, 30, and that's it, right? So, I don't know. It's something to maybe chat with Ceph folks. Is this expected? Is it really not able to scale? Maybe there's something wrong in the setup. I did something wrong. Maybe that's one of the next slides. More numbers. Latency. To give you real numbers on that, I've told you it's slower. Here you see the actual numbers. So where's CityDB? CityDB is green, so it's down there, right? So it's not 0, but it's certainly it's millisecond. And so it's the beginning. It's less than a millisecond. Right. Can you hear me if I'm talking to the side here? No one is complaining, so it seems to work. Okay. And the other ones, I mean, maybe that's usable. Maybe that's 10 or 20 milliseconds, and then, oh my God, okay, the other ones go up. FoundationDB then at some point, 512 clients, it also starts to ramping up. But I said those were small clusters, just 3 nodes, not tuned at all. I mean, this was literally the first time I've been working with all these databases, so I might have screwed up the setting, right? Who knows? So that means, no, later slide. First, maybe anyone is interested, so how did I do this? Getting Samba and the distributed database talk to each other. So in Samba, we have what we call dbrep, which is a pluggable abstraction where it's an API where Samba just calls into the dbrep API, and then you can have configurable backends. Volker has a question or a remark? Lunchtime. All right. I'm close to being finished. So look, it's on slide 16. So there's not too much coming, right? Yeah. Okay, so I will probably just skip this. In case you're interested, just ask me, right? So I think the more relevant part is probably this one, right? So I got help. Great. Thanks, Yule, who implemented the etcd backend in Python. And thanks to Samuel, who has implemented the Ceph backend. That's the only one that, because they don't have a Python API. So, and then of course I was happy. Yeah, Samuel had been working on a backend for Samba DB Rep for Ceph routers a few years ago. So I took that. So thanks a lot. That helped me a lot to test those out. Just quick numbers on how big is the overhead going via this DB Rep backend that is basically using Python C bindings to call into Python. So the scripts that I wrote for all the databases are written in Python besides Ceph, right? So what is the overhead going from C to Python? And then in the case of TDB, so TDB is our default database on a single standalone server. That would be C if we do it by default. And so I wrote a backend for this DB Rep C Python script. So we have Python bindings for TDB, which I call PyTDB. And then that again called into the C layer of TDB. And the overhead, as you see, is something like 10%. So it's not that bad. So I wouldn't probably use that in the end in production. If we settle on one solution, we would probably then write that in C. But for prototyping, so we know the overhead is not coming for implementing the backends in Python, right? At least only 10% of it. So a few conclusions. The winner is, as said before, currently it seems there's really only one distributed scalable database out there that could be used for such a use case, right? That is a database that is strictly consistent. That is supposed from if you read the documentation from FoundationDB, it's supposed to scale to a lot more nodes and to a lot more transactions per second, right? But might be marketing, right? So we might better do more tests there on larger clusters and not only three nodes. Of course, another possible would be, okay, maybe we just write our own. If the other ones are not really that performing, it's Java crap, and we want to do C, or maybe we want to do Rust or something like that. But the thing is, writing a distributed scalable database, it's hard. It's probably one of the hardest things you can do, right? You can start simple. You can use consensus algorithms like Paxos and Raft. That might be doable. That's what etcd is using. That's what many students at university learn if they take a distributed databases course. Then they go, okay, implement Raft and Go. And after a few days, they're probably done, right? But as you've seen, etcd, well, it scales. FoundationDB uses a different approach. Is able to scale better. And all these consensus algorithms are not the last word. So research is ongoing. And there's this distinction between leader-based consensus algorithms, which are Paxos and Raft, and leaderless consensus algorithms, which are supposed to allow more parallelism than going through a single leader bottleneck, right? Not to mention having then also to implement features like data center awareness, region awareness, and stuff like that. So maybe there's some hope. At the end of this year, Apache Cassandra version 5.0 is going to be released. It's still going to be Java, so I don't know. But it will implement a new consensus protocol called Accord. And that has some very interesting properties. It's leaderless. It's also allowing transactions, which is used in Cassandra. It's not only something that you would use in a key value store. It would also allow transactions and so on. It should allow better scalability. and this is going to be out at the end of the year, and yeah, I'm really looking forward to when it comes out to be able to play with that.